So what I'm going to talk about today is a piece of that whole perspective, particularly from my own perspective in material science. As a material scientist, what do I think of these materials and what can we do with this? What are the challenges? There's a large amount of work in the electronics area, optics. I won't probably touch any of those. But these are a very fascinating material. These are a new type of building blocks that we can play with. And that has been our fascination for the many years, the previous years. And you will see a large number of examples as I go through this, that it is really indeed a very unique material. Graphene, again, the title of my talk is Graphene and Beyond, and I'm going to talk mostly about how people started with graphene and how we are thinking ahead of a large number of different possibilities in terms of compositions. If you think about these kind of materials as 2D building blocks or units, then there are all kinds of possibilities, and you can think about these layered materials in general. And most of the layered materials that are traditionally known are based on a typical composition, a single composition. And these are interesting materials because they are very well bonded within the plane. They're very stiff material. Most of the time, all the bonds are satisfied within the plane. But the interlayer spacings are, rather large. The interlayer interactions are pretty weak. So you are in a position to actually pick and play with these individual layers that make up these layered structures. And that has been the real story behind graphene. If you think about, how this material was invented, they were essentially trying to peel off a layer of graphene, and it was pretty easy because it's known that graphene could be easily cleaved from a graphite structure. I used to work on carbon nanotubes for a very long time, and in fact, if you think about it, the whole area of carbon nanostructures, starting with fullerene and nanotube and graphene, it kind of took a reverse direction, because graphite had always existed, and it would have been much more intuitive for somebody to actually pick a layer and look at it rather than starting with fullerenes and going to nanotubes and graphene. But inventions are not done in any particular sequence, so that's a perfect example of how things happened in that area. But if you think about it, there are a large number of these materials that are layered, and there's now enormous possibility of looking at all these different structures. Some of them have been known. The graphite is a well-known material. Boron Nitride is quite well-known. A large number of dichalcogenides has also been very popular when people looked at nanostructures. Today, Reshef Tene talked about all these, spherical and tubular shapes of dichalcogenide materials. But now the field is slightly different in the sense that we are trying to create new types of layered structures, starting with some of these units that you could pick and choose from this set of materials. And of course, there are also some materials like borocarbon nitrides that have been less known, but there's a lot of possibility in there as well. Now, going back, this is a question that I want to answer through this talk, or at least try to answer. If you have these large number of these compositions that exist in this layered format, and if you are able to pick, a layer by layer from these materials, then I have this possibility of mixing them combinatorially and building new types of materials, which never really existed before. And that is a real fascination as far as I'm concerned. Of course, you have to really figure out ways of creating these individual units in a systematic and realistic manner. But the fact that you are able to create new materials using these building blocks really brings us to a large set of possibilities. Now, of course, in many of these nanostructures, the electronics have been the driver, so it would be not appropriate to kind of skip that, although I won't talk too much about this. But when people are talking about, electronic materials, there is, of course, the roadmap that they are always seeking to find new materials with exciting properties. And graphene was one of them because graphene showed an extremely high mobility for electrons. But of course, graphene has certain disadvantages. But if you think about this whole set of compositions that essentially span the entire breadth of band gaps and electronic structure, then you really have the possibility at some point of time to build things like all two-dimensional circuits. And that could be the long-term perspective in this area, where if you are able to manipulate and if you are able to engineer these different compositions with different characteristics, insulator, metal, semiconductor, then you might be in a position to build all 2D circuits. So again, we'll wait and see how that happens in the next several years to come. Now, going even beyond that, there's also possibilities of creating engineered structures even within a single atomic plane. You could create modulated compositions, and again, I'll show you some examples of that. That there is possibilities of mixing large number of possible domains within an atomic layer and creating, again, very, very different types of materials with sharp interfaces, which could be, again, part of this whole game of creating two-dimensional circuits. This is actually a list of things that are part of a big center that I'm part of. Again, it is funded through DARPA and SRC, and there's a large number of industries involved. Again, trying to see where we are going with many of these materials. And you can see, it's fascinating from a materials point of view. There are lots of issues that one has to address. How do you really think about scalable growth? How do you think about defects in these structures? How consistent these structures could be when you're trying to make devices. For example, the contacts could be a big problem. And what are the interesting properties that these materials would produce? How good are these as photodetectors, or how good these are for FET transistors, how good these are for energy storage materials. So there's a large set of opportunities here, large set of challenges here. So if you think about this, we are not really looking at just one material. When we were looking at nanotubes of graphene, we were looking at a specific material, but now the whole spectrum has changed, and we are looking at a large number of compositions, and each system seems to behave quite differently. So it's a real a challenge to address this from a generic point of view, although I'm going to try to do that and give you examples that kind of is generic, and it probably extends to other systems as well. Now, a real breakthrough happened a few years ago when the Austin group figured out how they can actually grow graphene material over large area, consistently using metal substrates like copper and nickel. Before that, most of the experiments were relying on this idea of peeling layer by layer from naturally occurring graphite, and that was a real pain, and that was certainly not scalable, or that was not going to be the real thing. But this has really changed the scenario, because people realize that you could in fact directly grow using vapor phase techniques a very large area. Even there's been companies demonstrating roll-to-roll manufacturing of graphene. So that really puts us in a different perspective, because you can really think about scalable manufacturing of large number of devices. Not only that, you could even think about creating very controlled thicknesses for these materials. You can have monolayer, bilayer, tri-layer, and these are easily characterized by global techniques like Raman spectroscopy. So the whole business of growing and characterizing became extremely easy, so that you can, in a systematic fashion, build these materials for various purposes. So that was, I think, a turning point in this type of research. And over the last few years, people have demonstrated all kinds of possibilities, and I'm focusing on graphene right now, basically being able to grow using solids precursors, liquid precursors, gaseous precursors. You can grow them on any substrate that you would like. But still, some of these growth techniques suffers from the fact that you can only grow them on metal, and you have to transfer onto an insulating substrate in order to make devices. But again, I think this shows the evolution of this whole idea of growing monolayers by vapor phase transport, and that has had a significant impact on this field. Whenever you're trying to grow something from nucleation growth process, you're also going to end up with some defects, and defects obviously become important. And if you, again, track the progress of this field, you will see that the best numbers that people have obtained for mobility and so on has been on larger domains that are obtained from this field of natural graphene. And the reason for that is when you grow this by vapor phase technique, the character of the material is different. You end up with a lot of defects, things like grain boundaries, that has a huge impact on its behavior. So on the one hand, the technique of growth on large scale by vapor phase transport has dramatically impacted the field. We are still struggling in the sense that there are defects to deal with. And one of the basic issues that people deal with now is how to grow very large domains, single crystal domains that could be, again, that could provide consistent results in this area. Now, almost everything has been done on graphene. If you think about all the stuff that people have done over the last few years, and it's almost deja vu for me because almost the same thing happened in nanotube area as well. People promise all kinds of things, super thin, super strong. If you have recently looked at the news release of coming from RISE, of course, some of these graphene material were stopping bullets. If you look at another recent work, the amazing proton transport on these membranes. So there's beautiful things that's happened with this material. And in addition to being very strong, at least from the in-plane strong bonds, you also have flexibility because it's so thin, optically transparent, conducting, all these amazing properties for graphene. Unfortunately, the one thing that it is not is that it's not a semiconductor. Right? So that is a real problem because it's a zero band gap metal. And a lot of work that goes to trying to create a graphene-based device is based on how you can introduce a band gap. Right. So again, the perspective I'm going to give is not just for electronics, but if you look at electronics per se, then this is a real problem, and I think that we're still struggling with that particular problem. Let me talk a little bit about the devices. Of course, this is, as I am emphasizing again and again, the biggest driver for many of these materials has been electronics. So it will be kind of unfortunate if I don't mention that at all. But again, what you see is that the behavior of many of these electronic devices based on graphene is not really consistent. It really depends on what substrate you put these materials on. In fact, if you look at this this chart, you'll see that in order to get to close to the predicted theoretical limits of mobility, you really have to either suspend this material and create devices that are from the suspended graphene, or put them on a substrate that looks something very similar to graphene. And hexagonal boron nitride is an interesting material that is isostructural to graphene, very flat. So in order to really build the best devices, you have to have compatible material. So many times when you think about graphene-based or 2D material-based devices and structures, you are going to think about a broad range of materials that have similar formats, similar morphologies. So, hexagonal boron nitride was really a boon to this field because people proved that you can use that substrate in order to get good values for device performance. Now, again, electronics is not the only thing. The one thing that strikes you is the graphene is really super thin. It is the thinnest material you can ever get to because it's flat and it's atomically thin. And there are many other possible devices you can make using these, which could add value to this entire gamut of platforms that you might build with 2D materials. For example, you only need a layer of graphene to make a supercapacitor. And the same story with molybdenum sulfide. This is a simple demonstration that you can actually create a small gap and put a electrolyte, and it would work reasonably as a supercapacitor device or energy storage device. Or, this extreme thinness manifests itself in various other phenomena, which is not very intuitive. I've already mentioned, and many of you are aware, that graphene is extremely transparent optically. For a wide range of wavelengths, it is quite transparent. Only about 2% or so light is absorbed. But it seems to be also transparent to certain other phenomena that is quite fascinating. For example, it seems to be that if you put a layer of graphene or 2D materials on a substrate, that substrate still retains the same wetting characteristics of if you're dealing with some interface between a solvent. So those things are fascinating because you can think of some new types of application where these graphene type of coatings could be totally non-invasive, and you could still get the same kind of interfacial characteristics with the substrate that you are looking at with any solvent that is interacting with it. So there are some very, very unique phenomena simply because of its extreme thinness. Or, the surface itself is quite unique. As I said, it's the flattest material you can ever get. It's not just flat, but it's also very, very stiff material because the bonds are very stiff. So this is an interesting experiment that was done in Raphael Tadmore's group in Lamar University, where they have this facility to look at the movement of water on surfaces. And what he finds is that typically, most surfaces have what is called a resting time, and it reaches a plateau after a certain time. And this is because as you're trying to move solvent or water on the surface, you have some reconstructions on the surface that is happening. But it looks like something like a graphene layer or boron nitride layer is almost invariant with this resting time because there is absolutely no surface reconstructions occurring as you're trying to move or drag water droplets on the surface. So because of the very nature of the bonding, the stiffness of this bond and the flatness of this material, you have an extremely different type of surface, and which is very unique. It can only happen in materials like graphene. Now, I mentioned that the biggest problem with graphene is that it does have to have a band gap, and that somehow it doesn't exist. So what do? People have been trying to actually create ribbons and quantum dots and so on from graphene, quantum confining the dimensions so that you can introduce some band gap. But of course, there are also some other issues. For example, the edge that you expose when you're patterning seems to have an impact on the properties of this ribbon that you create. So there are some issues there as well, but there's been a lot of work dealing with how you can create dimensionally confined structures from these type of materials. The one thing that is great about graphene is it's two-dimensional, so you can actually do top-down patterning to create these low-dimensional structures. Similarly, quantum dots. There's a large number of work related to creating quantum dots from these materials so that you have a clear band gap. Of course, the band gap arises not just simply from the confinement of the size, but also from some chemical groups that get attached to these surfaces because you are breaking it down using some chemical methods. But nevertheless, you can have a clear change of band gap as you decrease the size of this material. And it's also valid for many of the other two-dimensional materials like the dichalcogenides and so on. So there's large amount of work now trying to replace the traditional quantum dots with these type of two-dimensional quantum dot material. Now, bringing the size down or nanostructuring these graphene type material, but in addition to that, also electrically gating, which is equivalent to some kind of doping process, you can also introduce some band gap. And by doing that, you can even increase the absorption of light that passes through. So by really playing around with the size and the gating, you can really change the absorption of light. Again, this is to do with the plasmonic manipulation. You can actually control some of these absorption. And if these kind of structures were to be used for photovoltaic applications or so, you have to have better absorption, and that can be done by nanostructuring as well as gating. So there's a lot of materials processing that can be done to these materials to create band gap, to introduce different types of absorption phenomena in these materials. Or you can think about combining different types of nanostructures, which is a little bit more complicated, but it's certainly feasible. And here is again an example where we have actually taken graphene layers and sandwiched these plasmonic antennas that were fabricated in Naomi Haller's group at Rice. And these would behave in combination as a very good photodetector because the hot electrons that can be transferred through these antennas, they can easily be transported at high speed on graphene because of the high mobility of electrons. So these kind of combinations of dimensionalities or structures at both 2 dimension as well as 0, 1 dimension can provide you some interesting devices. And in the long run, many of the nanotechnology applications that we'll see will come from these type of marriage between different types of nanostructures. These are things that have not been done to the extent it should be. But I think combining 2 different types of nanostructures would allow you to enhance the performance of many of the devices that you're building. Now, of course, graphene, so far we have talked about this pure graphene material, but also there is a large set of compounds that are based on graphene, but they have been chemically modified. And the simplest one would be something like a graphene oxide. You take carbon and oxidize, you essentially start getting all these functional groups onto the surface of these sp2 hybridized units. One problem with that is that typically, an oxidized carbon, oxidized graphite or graphene, is a very inhomogeneous structure. There's no real knowledge about how these functional groups are distributed on the surface of these units. But when, at least from the point of view of graphene oxide, people are getting a better feel of how these these functional groups are distributed, because now you have, an entity that can be better understood from its size as well as in, the thicknesses. So it's much better than graphite oxide because I think the structure is better known now. And even, there are a lot of work trying to figure out how you can specifically introduce one functionality versus the other. Can you remove, after oxidation, certain functionalities? So there's a very interesting field of how you can controllably engineer this chemistry on graphene layers. And we have also done quite a bit of work on that. And again, there are a large number of possibilities. Oxidation is not just the only option where you can change the behavior of graphene layers. Again, it introduces a band gap, and if you oxidize it all the way, you can actually make it insulating. So there's a lot of possibilities by changing the chemical nature or changing the sp2 nature of this basic unit. Fluorination is another thing. Hydrogenation is yet another one. So again, people have been playing around with the chemistry of these materials to, again, change the electronic character all the way from metallic to semiconducting to insulating. And I think, to some success, things like fluorinated graphene oxide is quite interesting because it shows characteristics like super ampliphobicity, non-linear optical characteristics and imaging and all kinds of things like that. Now, I mentioned about GO, but there's also this reduced graphene oxide, which, again, is similar to graphene, but not exactly graphene. And, this can be done through solution techniques, so it's much easier to create in bulk forms. And the combination of GO and RGO allows you this powerful, metallic insulating material combination. And we have done several experiments. Many of the other groups have also been pursuing this to try and create devices that are based entirely on the different formats of functionalized graphene. So if you have graphene oxide, reduced graphene oxide, you can in fact build capacitor devices, supercapacitor devices, which are quite fascinating. In fact, the GO itself seems to be an ionic conductor, especially in the hydrated form. And now people are also looking at the permeability of graphene oxide to various gases and so on. So I think there's a broad range of interest in this functionalized graphene as well. Now, the graphene lattice is also quite interesting, and over the last many years, people have tried to change the character, not by functionalizing chemically, but by introducing dopants into the lattice, substitutional doping. The simplest elements that have been tried, and again, there have been several talks in these sessions here on how to substitutionally change graphene. One of them is certainly introducing things like boron and nitrogen. And of course, we still are not very clear about how these, substitutions occur and where these substitution elements go and sit. You still can, certainly see that certain amount of these elements can get into the lattice. And some of these materials are fascinating. The nitrogen-doped graphene has been known to be very catalytic. The boron actually is known to crystallize the graphene material better. So each of these have its own catalytic effects. And there's generally some knowledge, but not entirely, how these materials are constituted. For a long time, we have been also looking at these type of systems, and doping in graphene materials is very different from doping traditionally, for example, in a semiconductor material. Because many times what happens is that the dopants create domains that segregate and form embedded domains in the graphene lattice. So, for example, the boron carbide is actually a planar phase which can get embedded into a graphene lattice if you are trying to put boron into graphene when you're making them. So there's all kinds of strange effects of doping that happens in graphene compared to what we normally know about doping. And in fact, this whole phase diagram of boron, carbon, and nitrogen, and maybe you can also think about a quaternary system where you have oxygen, is really fascinating because in this phase diagram you have pretty much everything you need to make a two-dimensional electronic circuit. You have the carbon, of course, which is a metal. We have the boron nitride, which is an insulator, and you have many of the phases that have been thermodynamically, theoretically predicted, which are in the semiconductor range. So if you can manipulate these different phases, you can basically build the whole electronic devices using these and these alone. But again, as I said, the problem is that if you're trying to make some of these phases, like BNC or BC, it doesn't really form thermodynamic phases, at least under the conditions that we use for synthesis. And what happens is that instead you end up with this patchwork of different domains, because the boron and nitrogen like to be together, the carbon likes to segregate. So you essentially get this segregated picture of these domains of these phases. And still, I think people are yet to show real thermodynamic phases that contains all these phases. But it's a fascinating phase diagram for sure. We have been creating, again, using the similar techniques as graphene growth, we can actually produce these bilayer systems or trilayer systems of these BNC. But again, as we characterize them better, you see that they are all segregated domains within these planes. But these segregated domains could be also interesting, because if you can engineer them in the right geometry and right size, then you can really create these beautiful hybrid atomic layers that again has never really existed. And if you were able to follow this pathway and basically create your entire circuit on this two-dimensional atomic layer using this approach, then you can really get into business. So again, a lot of theoretical predictions on how some of these structures could be embedded, and the interfaces could be contiguous and straight and sharp. So it's a fascinating area, because this boron nitride and graphene, they're both isostructural, so they are almost non-distinguishable from a structural point of view. But one is an insulator, one is a conductor. And again, following that particular idea, we have been in recent years trying to design different domains of different sizes and shapes within these atomic layer matrices. So you can start with boron nitride, for example, and etch away some of this boron nitride and regrow the graphene in that region, and essentially build up any kind of circuit or any kind of domain that you need in terms of shape and size. And basically stay within this atomic layer. And the good thing is that these interfaces are quite strong and continuous. So once you make those, once you grow those, you can actually peel them off and put them on a different substrate. So they're very robust, hybridized atomic layers that can be utilized for various purposes. And you can go to very thin regions as well. So these growth can be sequential, and they can really produce very fascinating structures, things like antennas and other simple devices, but also maybe complicated devices. The boron nitride is also another material in this family. Again, as I said, electronically is very different, but structurally is very similar to graphene, which has got fascinating properties. And boron nitride is a very useful material. People have been using it for oxidation resistance and so on for many years. And it's one of the least reactive material that you can find. And we have also been playing around with boron nitride in order to create these contiguous large area films. But of course, boron nitride is a little bit tricky, because the phase diagram of boron nitride is slightly different from that of graphene, and the cubic phase oftentimes gets more stable. So many times when you're trying to grow them, you end up with a lot of sp3 defects, which does not allow you to make nice continuous monolayers. So boron nitride growth, again, a lot of people work on this area, and there has been some progress, but to get really a single layer of boron nitride is quite tricky. But if you have a few, that's actually some characterization, if you actually make a few layer boron nitride that are continuous, then it could be very, very interesting. Here is an experiment that shows that if I put about 5 nanometer thick boron nitride continuous film on metal surfaces, the metals can withstand oxidation up to about 1,000 degrees in air. So these are really very, very robust layers. Although they are so thin, almost non-invasive in many ways, they can be extremely useful in terms of protecting surfaces. In fact, we are in fact building a large center based on coatings of these 2D materials for various purposes, not just for oxidation and corrosion, but also for areas like catalytic coatings and so on. So, ultimately, the area that these type of materials would find use could be these type of extremely super thin coatings, which could have a large range of possibilities. Now, again, these materials also are good thermal conductors, both boron nitride and graphene. So people have been trying to use these as fillers for composites or even fluids. Here is just an example to show that you can increase the thermal conductivity quite dramatically by introducing boron nitride or graphene into various liquids. In this particular case, we were looking at oil, transformer oil, because they have a serious problem of increasing thermal conductivity. And normally, most of the fillers that you put into these kind of fluids, they either settle down, so the shelf life is very low, or they actually increase electrical conductivity, which is not which is something that you don't want. So something like boron nitride seems to fit the profile very well, because they not only increase thermal conductivity, but they also don't increase electrical conductivity. And we have done quite a bit of work in this, and in fact, this technology is being commercialized. So, very simple idea, very simple application of 2D materials could be to create things like filled structures that could have very high stability and that serves the purpose of perhaps increasing thermal conductivity. Now, I mentioned that in a single layer graphene, boron nitride is rather difficult to make, but you can always play some tricks and create interesting reactions that would allow you to convert graphene into other compositions. Because graphene can be grown very nicely over a large area and could act as a perfect template. So here is an interesting example where we have managed to convert boron nitride layers into graphene layers into boron nitride layers. In fact, this is something that is already known in the nanotube community. A lot of people are trying to create boron nitride nanotubes from carbon nanotubes by using this type of high temperature reaction. So one could think of essentially starting with the graphene layer and basically using this high temperature reaction to convert them into other compositions of boron, nitrogen, and carbon. And in fact, you can do this in a sequential process and ultimately end up with a layer, a monolayer, that has the boron nitride, which is insulator, graphene, and the BNC systems that are semiconducting. So we are reaching close to the possibility of creating a real electronic circuit within a single atomic layer, again starting with graphene, because you have we have shown that you can in fact create all these different compositions with different band gaps within this atomic plane. So the goal that I started talking about of having a complete functional device built on a single atomic layer, whether electronically that that would perform much better, I'm not in a position to say, but certainly you can really demonstrate that you can build functional devices at such thicknesses, that monolayer thicknesses. And the same idea of conversion of carbon into boron, nitrogen, carbon systems can be implemented on any kind of systems. It doesn't have to be graphene flat layer. It could be a graphene ribbon. And we have been actually looking at possibilities of creating these hybrid nano ribbons of carbon, boron, and nitrogen, and create these type of three-dimensional constructs that could be very interesting for things like the oxygen reduction reaction. In fact, I already mentioned that things like nitrogenated carbon or nitrogen-doped carbon can be pretty good in terms of these type of applications. The carbon nitride layers are also fascinating. Carbon nitride, again, theoretically it has been predicted for a while, the hexagonal form as well as the cubic form, and experimentally very few people have actually managed to see that it can be grown in a perfect way. So, even things like carbon nitride has been well known as a catalyst. And in fact, there's been a lot of talk about replacing noble metal catalysts with these type of nitrogen-doped carbons, which probably, you still need some optimization. But certainly, these are very, very interesting two-dimensional layer structures. The carbon nitride, because of the lack of central symmetry, because there are these holes, triangular holes in the structure, it also becomes piezoelectric. In fact, we have in fact grown layers of carbon nitride on a substrate, and using some atomic force microscopy technique, we have managed to show that this can indeed be piezoelectric. The piezoelectric coefficient is about 0.5, which is close to that of quartz. So it's not that small as well. So there are all kinds of fascinating properties of these individual layers. The doped layers, even though carbon could be, pure carbon could be quite fascinating, I think it becomes much more richer as you're starting to play with the lattice, with the chemical functionalization and so on. Now, the next level of complexity would be to think about what I initially started talking about, and that is to create these artificially stacked structures where you pick and place different atomic layers and build up your solid. Of course, we have demonstrated that, and several people have done that as well. But the vapor phase transport is probably not the best technique to really build large volume solids. It could be very interesting for very thin stacks for specific applications, but for large area bulk materials, that one has to think about some other options. And even a simple stack like graphene, boron nitride, graphene is quite fascinating because it would make the thinnest capacitor that anybody has made. And in fact, we see that when the thickness of the dielectric of boron nitride goes below a certain thickness, then the capacitance goes high pretty quickly, and it cannot be explained by the usual classical electrodynamics. So there's lots of possibilities that you can play with these type of sandwich structures. As I said, the best way to organize some of these layered materials, multi-composition layered structures, would be using some chemistry approach. And in fact, this is a very, very basic experiment where we took exfoliated graphene and exfoliated boron nitride and simply mixed it together in solution, and then basically graphitized it, precipitated it and basically annealed it, and you get this composite material. It's a mixture of boron nitride and graphene, and you have domains that are in the hundreds of nanometers that are kind of stuck together, again a patchwork, but also there is a grading compositional change throughout the material, and you still see some interesting effects due to this simple mixing process. Spectroscopy shows some interesting additional electronic states coming in because of this interface between boron nitride and graphene. But if there is a way to really order these structures, some kind of periodic Vanderwall solids by this kind of mixing process, then you really are going to be able to make entirely new types of material in bulk. Now, I haven't really talked much about this transition metal dichalcogenide, so let me spend a little bit of time on that. This has become, again, this almost taken over from the big graphene groups, partly because there's a large range of compositions available. They are semiconductors, and they could be also grown pretty easily. In fact, the growth is even easier than what you can do with graphene. And again, several groups have focused on the idea of growing these into large domains, which could be useful for experiments. And one of the things that we did recently was to kind of use this molybdenum trioxide precursor and evaporate them and along with sulfur, and it forms these beautiful monolayer. And again, the monolayer of molybdenum sulfide is more like a trilayer with 2 sulfur and 1 molybdenum in between. But they can be grown over large scale in a reasonable way. And again, this type of growth always produces grain boundaries, and grain boundaries are interesting in these two-dimensional materials, broadly speaking, because they are essentially these topological defects that exist in many of these two-dimensional structures. Very curiously, the grain boundary structure looks strikingly similar to that one finds in graphene and other materials, all these 5-membered defects and 7-membered defects. So it's kind of interesting. And the grain boundaries in these materials have also been predicted to have their own character, like magnetism and so on. A lot of predictions from theory. Experimentally, it has not been proven. But I think if there is a way to manipulate the kind of grain boundary structure you have, then you can really play around with transport through these boundaries. And as I said, it's reasonably easy to grow very large domains, single crystal millimeter scale domains of these type of materials, and that allows us to get good devices made, and that has been again a very good thing. Now, one of the problems with a lot of these growth are that they are done at very high temperature. So if you're thinking about using this for electronic platforms, then those temperatures are too high, 800 degrees and above. But we have been also seeing some positive trends where you can decrease the growth temperature by introducing some other elements into the picture. But again, there's always a danger of some of these materials getting doped into the layer, and that could create issues as well. But nevertheless, I think it's interesting that you can manipulate the growth processes to some extent. Now, one of the issues that we find in the growth of transition metal dichalcogenides compared to graphene and boron nitride is that many times these domains, as they grow, get pinned by some nanoparticles, and then it doesn't really complete its growth. And there are some curious effects. For example, in this particular film that looks almost continuous over a large area is not really continuous. I mean, there are gaps. These are not really grain boundaries. These are basically gaps because the structures have actually stopped growing at some point. This has to do perhaps with this pinning that I mentioned to you, where these particles, and they also seem to be molybdenum sulfide, but not really this 2D structure. They seem to pin the growth around the boundaries, and then they stop growing. So there's a bilayer system. This has grown much larger, but this has stopped its growth because of these particles that end up as pinning sites. So there are many issues associated with growth as well, and I wanted to make sure that that's emphasized. Now, doping is also very much possible, and people have shown doping in transition metal dichalcogenides in nanoparticles, other systems of TMDs. Even in this monolayer, doping is certainly very, very feasible. And unlike the graphene system where the dopants were segregating into domains, here there's a very nice uniform distribution of dopants throughout the system. So we have this is an example again of selenium replacing sulfur, and the replacement could be almost complete. You can actually get the entire spectrum of concentration change from molysulfide to molyselenide. And we have done some detailed work in showing that these dopants are now well distributed throughout the lattice. In fact, the preference for selenium is actually to form the sulfur-selenium pairs first before actually it replaces completely. So there is a very nice diffusion distribution of selenium as you dope into these kind of systems, which is very different from the graphene system that I mentioned to you. Now, by doping, you can change the band gap to some extent. Here is an example to show that the selenium doping allows you to play with the band gap to about 100 MeV or so. And that could be useful in some scenarios, maybe not specifically for this molybdenum system, but maybe in some other systems. In addition to the dichalcogenides, we have also been growing some monochalcogenides, like gallium selenide. And again, the reason why you have all these materials now interesting is because they fall into the different band gap spectrum. And there are some interesting materials based on single chalcogen atoms, and again these are also now possible to be made into thin monolayer films. There are 3 component systems which are also interesting. In fact, this one is a very interesting one because its band gap is rather low, and also one thing you see is that many of these monolayers, they go from indirect to direct band gap as you go into the monolayer systems. So there's lots of possibilities if you can choose the right system for the right applications. And copper indium selenide again is a material that has been used in photovoltaics and so on. So it's interesting to know that you can actually grow them in monolayers. As I said already, the substrates make a big impact on its electronic behavior. You already saw that picture where if you put graphene on silicon oxide, your mobility goes down dramatically. But if it's not sitting on some other substrate like boron nitride, it's pretty good. So again, there is a large number of possibilities to create devices on different types of substrates. And here is a demonstration where we are able to place the molybdenum sulfide on self-assembled monolayers, soft substrates. And depending on the terminations of these self-assembled monolayers, we can change the electronic character of this material. The transport behavior changes quite dramatically. The conductivity changes. The mobility changes. And that's partly because of this charge transfer between these terminal groups and the Tmd layer. And again, this is something fascinating because you can not only put or vary the compositions of the self-assembled monolayers, but you can also possibly manipulate the dynamically the structure of these self-assembled monolayers, so that maybe you can really control the transport in a dynamic way on these 2D materials. So here is something that shows that clearly there is a change in transport characteristics as you go from one SAM to another SAM. The other possibility, because these are flexible, is to be able to tailor the band gap by strain. The strain engineering has been well known in the semiconductor industry, and here you have a much better option because these materials are much more flexible. So again, we have shown evidence, we have seen evidences to see this change in band gap and change in conductivity as you change the flexibility, as you kind of start bending them and so on. The goal, again, the fascinating goal that we have is to be able to build these stacks of different character, different compositions. And I think that's what a lot of people are doing. If you were listening to the Symposium J, a large number of the talks were related to this ability to kind of engineer different compositions and build this three-dimensional stacks of two-dimensional material. And I think this whole idea is fascinating because you're really building these Vanderwall structures that have very new character. It's never existed before. So we have had some success in some of these materials that we create, like molybdenum sulfide and tungsten sulfide. Now, when you're trying to stack different layers, it's not just about putting one layer on top of the other. There's also subtle changes depending on the orientational order, the stacking sequence, and of course the interlayer spacing, and there's several other things that you can manipulate as you're building these type of structures. Many times, if you are going to transfer layers one on top of the other, the interfaces are not very clean because transfer process always involves solvents and so on. So I think the best way to create some of these stacks is to directly grow one on top of the other. But that, once again, is challenging. As I said before, you cannot really build up thicknesses by that technique too much, right? So one has to compromise on what exactly you need. And here is an interesting example, a recent example, where we have shown that one could use multiple precursors at the same time to grow these kind of stacked structures, which are very good interfaces, which are very clean, and also which are very preferred stacking sequence. And in this particular case, between molybdenum sulfide and tungsten sulfide, we have a clear 2H stacking when this growth is done at higher temperature. And this actually a lot of characterization proving that the stacking is specific. And again, it's very clear. The spectroscopy that we do on these materials shows clear differences between these as-grown stacks versus the transferred stacks, because obviously when you transfer, you cannot keep the orientation, and you cannot also remove all the impurities that are there. So this whole idea of creating or building up three-dimensional structures from 2D building blocks is fascinating. We have a long way to go, but we are now learning how some of this engineering could be done one by one. And this PN junctions, and I don't have too much time to go into this, but people have started to make PN junctions, because if you have a system like molybdenum sulfide, tungsten sulfide, one is N-type, one is P-type, and it's very easy to build these type of junctions, and they behave essentially like a PN junction. The only issue is that the absorption in these materials is very small, so one has to manipulate how you can improve the absorption in these. Another system, the selenide system, again, if you start to grow multiple layers rather than bilayers, then you start getting these composite layers that are stacked together. So each of the layers themselves may have multiple compositions, but also the stacks are now different character. So you can essentially end up with a very composite, complex system, which again, could be of some interest. And again, this is a very new thing, and people are now starting to study how these interfaces change, how the electronic properties of the interface change as you change compositions, and so on. So a large number of possibilities exist in building these type of new stacked structures. And also, again, a lot of propositions by theorists and other electronic folks trying to say that these type of devices could be quite interesting, particularly because there's no real broken bonds across interfaces, so there's very little scattering, very little traps. They maybe perfect electrostatics, very little short channel effects. So there may be many advantages of creating these type of materials compared to the traditional way of putting thin films on top of the other. One big question is, of course, because they are so thin, because every atom is exposed, is how stable these are, really. I mean, I think this question has to be answered at a reasonable time frame. And again, this is not just for these 2D materials. It's true for all nanostructures. We have been working on nanostructures for a long time. Perhaps carbon is a specific example where it is very stable. But many of these compositions may not be very stable. This is an interesting example of molybdenum selenide, which is monolayer, which we simply just expose to air, not doing anything, not even temperature, and it simply falls apart. There's some reaction going on between air and the layer. So, and there are many such issues which we are not addressing in a broader sense. For example, I've always been fascinated by this idea of contact between two materials of dissimilar electronic character. Basically setting up a galvanic cell, and the corrosion in these systems could be quite tremendous, quite instantaneous. So I think one has to also think about how stable these layers are in various environments and various conditions, if we were to actually get this to a level which could be practically very useful. I thought I'll just show you that because this is something to think about. A few last slides, I also want to mention this possibility of creating three-dimensional structures using two-dimensional building blocks, not in such ordered fashion that I talked about, which could be useful for electronic materials, but these could be useful for mechanical properties or scaffolds and many other things. And again, there's a lot of work in the past few years where people have been trying to create foam-like materials, very porous structures using 2D building blocks like graphene. And I'll show you a few examples. And again, there's a lot of stuff in literature, so I don't have to really show you everything. GO is an interesting material I already mentioned, and you can perhaps covalently link them using chemistry to build these three-dimensional scaffolds. And again, we have proved that there is covalent interconnections between these layers at the edges, and ultimately you can build very large solids that are essentially made of these type of building blocks, and very porous material. You can control porosity to some extent. So this could be a totally different approach to building porous materials from bottom-up approaches using these type of 2D materials as building blocks. Or even pure graphene. Again, several works in literature over the last couple of years. And these are fascinating materials because, these are all made of graphene-like layers, extremely thermally stable. They show absolutely fascinating thermoelasticity. They are, elastic to high strains at 1,000 degrees and maybe even to very low temperatures. So you're really building a new set of materials that are made from these type of stable building blocks, but with the right kind of porosity and so on. So again, it's a fascinating area. And you can mix and match again in these systems. You don't have to really build these foams with graphene alone. You can have graphene boron nitride foams. You can have materials that are distinctly different in chemical character compared to pure graphene. And you can even think about building hybrid structures with different dimensionalities, like graphene, carbon nanotubes. And they all show improvement in properties compared to this individual unit from which you can build. And again, if I've worked in carbon materials for a very long time. It always fascinates me to think that there are a lot of predicted structures out there which we have not been able to discover or build experimentally. And that could be the next generation of carbons. I think carbon, is a very practical material. So, if somebody asks you what all these nanostructures of carbon has done for you, perhaps, it's a learning process to build the next generation of carbons that could be really valuable for practical applications. And again, as we've seen already, carbon is just one element in this whole possible range of things that we can do. There are other materials. I haven't really talked much about oxides and borides and so on. There are many layered systems that can also be interesting. Here is an oxide carbon system. Again, these ribbons of vanadium oxide layers have been laced through with a graphene layer, which makes it a very good and interesting battery electrode material. Oxides are good as an electrode, but they are not conducting. So if there is a good way of weaving together the different materials in 2D so that you can embed different functionalities like conductivity, capacity, then you can really build fascinating architectures that could be of use. So let me summarize and say that the most interesting thing that has happened in this field is our ability to create in a reasonably scalable fashion these 2D building blocks. And the next thing to do would be to kind of build heterogeneous structures, either periodically or with less periodicity. And that, I think, would change the possibilities of materials in a big way. And it's not just about electronics, but it's also about many of the other applications that I hinted at, catalytic applications, composites, filled fluids. There are all kinds of possibilities if you can really engineer these nanostructures with this such thin building blocks. So I also want to acknowledge, we in fact started our basic work of this 2D materials with the Muri program from the Army Research Office. And I want to acknowledge that program because that really set us in this mode of looking at 2D materials as a major building block for material synthesis. And also, a couple of years ago, we had organized this workshop supported by NSF and Air Force Research Lab on 2D materials that goes beyond graphene. And that has kind of evolved into many funding opportunities and so on, which especially the US folks have been able to utilize. So I think there's a big community now working on this area. And let me kind of stop here and hope that in the future we'll be able to really engineer some of these materials with the right kind of character that you're looking for. And thank you for listening.